This is example 3.1.7. We're going to be taking a look at how we can figure out if a function has local maxes or mins, or maybe neither. And so we're going to start with the fact that we're given the derivative of a function and it's nicely factored for us. And so the first question is, can we determine all the critical numbers? And remember, the definition of a critical number is whether is all the x where g prime of x is equal to 0 or does not exist. Okay, so in this case, if we set this equation equal to 0 and solve for x, maybe I'll just do that up here. E to the minus 2x times 3 minus x times x plus 1 squared equals 0. So either the exponential function is 0, which it never is, right? So this part of the equation will contribute to the solution, or x minus 3 or 3 minus x is equal to 0. So that's one possibility. Or the x plus 1 squared is equal to 0. So that's another possibility. Good. So we see here that the critical points are either x equals 3 or x equals minus 1. Good. Now we can take these critical points and perform an analysis of them. So remember, the first derivative test says that we're looking for a switch in the sign of the first derivative. And so down here I'm going to go ahead and draw my number line. And I know that my critical points are at minus 1 and 3. And so over here I'll write down my derivative, e to the minus 2x times 3 minus x times x plus 1's quantity squared. Good. Now, the e to the minus 2x is always positive, so it's not going to change the sign of our derivative, so you don't really need to use that as part of our, because what I'm going to be doing here is just, excuse me, I want to see if the derivative is positive or negative. That's all the information I need here. So I can use some test points. So for example, how about if I test x equals minus 2? Well, if I put in a minus 2 here, this term would be a positive number, and minus 2 here, this term would be a positive number. Positive times positive is positive. This is positive, so everything's positive here, so I just say positive. Now a number between minus 1 and 3. So for example, x equals 0 is a test point that I could use. So if I put in a 0 for my x, e to the 0, that's equal to 1, so that's positive. That's 3, so that's positive. That's 1, that's positive, so everything's still positive. Okay, so by the way, do you see that the sign SIGN of the derivative did not change as we pass through the point minus 1 here? And so how about if we put in a number bigger than 3? So how about 5? 3 minus 5 is negative. 5 plus 1 is positive. 5 plus 1 squared is positive. So that's a negative times a positive times a positive. So that's going to be a negative here. And so therefore, the derivative switches between positive and negative. And so we're going from increasing to decreasing. Right? So therefore, there's a local maximum that occurs at x equals 3. Local max at x equals 3. Good. And similarly, nothing happens here. So the function just increases, it levels off, and then it increases, and then it decreases. So if you were to sketch a graph of your function g, what would it look like? Well, I don't really know what the height of the graph is, but I do know that before negative 1, it's increasing. Right? I should have drawn that a little better. Okay, there's 1 and 3. Good, so the function is increasing, so we might say it's increasing like this, and then it plateaus off, and then it's increasing again, increasing, still increasing, and then there's a local max here, and then it starts decreasing. So this is just a really rough sketch of what the function g may look like, right? Just in terms of increasing and decreasing. Good. So we have a little plateau there, and then it increases more here. Alright, so we see that there's a local max there. Of course, you could graph this, and you would get the same information, but you would get a lot more detail in a graph, right? So when we're doing a sign chart analysis, this is a sign chart, we don't really need all that information that's contained in the graph. All we're looking for is just to see if our derivative is positive or negative. Good. And using that information, then we apply the first derivative test to see if we have a local max or min. Okay, so we're continuing with another example here. This is actually activity 3.1.2. So I'm assuming that g is a function whose derivative looks like that. And so we want to perform our local derivatives test, or our first derivatives test, to see what kinds of local maxes or mins we might have. Okay, so first off, we will find the critical points. That's always the first step. By the way, sometimes these are called critical points. I think our text calls them critical numbers. But in either event, those are where the derivative is equal to 0 or does not exist. Okay, so right off the bat we see that at x equals 2, the derivative does not exist, so that is a critical point at x equals 2. And then the other two, if you set this g prime equal to 0, right, the first thing you're going to do is multiply both sides by the denominator. And so now either x is equal to 4 or x is equal to 1, right, for that to be 0. Good. So we have 3 critical points now, and now the other part of this is going to be the sign chart analysis to see if we have local maxes or mins. Good. So let's draw that out. And down below here, remember, along the axis, we're writing down our critical points. So we have a 1 and a 2 and a 4. Okay, and then we now there's several ways you could do this. We're really just interested in the sign of g prime of x. So we'll just go ahead and use our test point in the entire expression here. Doesn't look like it's be too hard to figure out. So for example, a number less than 1, how about 0? So that would be a negative number. That's a negative number. It's negative over negative is positive. That's positive, so that's positive. Everybody catch that? So this was minus 4 divided by minus 2, which would be a positive, and then this would be a negative 1 squared. So this term is always positive. Okay. How about a number between 1 and 2? A number that's bigger than 1 and less than 2. If the number is less than 2, the denominator is still negative. And if the denominator is less than 4, this number is still negative. So these two numbers are still negative. And then this number is positive, but it doesn't matter because you're squaring it anyway. So negative divided by negative is positive still. Good. Then how about a number between 2 and 4? Like 3. So if I plug in 3, the numerator here, 3 minus 4 is still a negative, but 3 minus 2 is now positive. So this is a negative number now, but this is still positive, so overall we have a negative number. Okay, so if you didn't catch that, we're just plugging in x equals 3 into that expression, right? So we had 3 minus 4, which is negative, and then 3 minus 1 squared, which is positive, divided by 3 minus 2, which is positive. Okay, so overall then it's negative. And then how about a number that's bigger than 4, like 5? 5 minus 4, positive. 5 minus 2, positive. 5 minus 1, positive. Everything's positive. Good. Now, we want to take a look at our analysis here. We're going from positive to negative, and so what's happening here is our function is increasing and then it's decreasing across the line 2. However, what's happening at 2 is we're told in the problem that we actually have a vertical asymptote at 2. And so graphically what's happening at 2, we'll just try it here. Yeah, you see your function's increasing here and decreasing here. And so you're ending up with a curve that looks like that at 2. So that's not going to be a max or a min there, local max or min. Okay. And then let's see. At 4, what's happening? We're decreasing and then we're increasing. And so we actually do get a local minimum there. So we do get a local min at x equals 4. And then how about at x equals 1? Yeah, it's increasing, plateau, increasing. And so nothing's happening at 1 either. Okay, good. So this was kind of the tricky one. We were told in the problem, I should have probably wrote that G has a vertical asymptote. At x equals 2. Right, so then the curve can break apart there, and so we don't get a max or a min there. Good. Let's see, we're also asked, what is the limit as x goes to infinity of g of x? Or g prime of x, sorry. So if we look at our g prime, it looks like we have a cubic function on the top and a single x on the bottom. So therefore, this is going to grow like a quadratic function. Remember, it's increasing when when x is bigger than 4. So this is going to be growing like a quadratic outside of this area here. So it's going to be going to infinity fairly quickly. Good. We won't sketch the possible graph of g. I think you kind of see what's happening there. The video is getting long, so we'll stop there. Next up, a few more examples.